Hey everybody, welcome back to my basement. We are going to do some series circuit problem solving examples. So here's what I want you to do right now. Get your hands on a physics reference table. Flip over to page 4 because that's all going to be all the stuff we're going to need for today. Get a calculator handy and some paper and pencils. We're going to be doing 2 problems all together, analyzing two different series circuits. This is going to give you the tools necessary to not only analyze how series circuits work, but really all circuits that I could possibly give you. By following the problem solving strategy I lay out here, you'll be able to really answer any types of problems. Everyone ready? Let's get started. So last lesson we learned about series circuits, which just means that each component is hooked up. It's a nice fresh new marker. Each circuit, each component set up so the current has to flow through each one sequentially. There we go. So here's an example of a series circuit. 3 resistors hooked up to some kind of voltage source. Now keep in mind, I could have drawn the circuit like this. I always want you to think, like, is this a different circuit from the one set up? This is going to have the same exact electrical properties as this circuit here. The only difference is it's all along one side. But in both cases, the current has to flow through each component before it flows back to our voltage source. So we're going to keep our first setup. And let's do an example with, let's say, a 12-volt source. Pretty standard for some tabletop electronics. And then each one of these is going to be 2 kilo ohm resistors. All right. Now the strategy I set out here will give you the tools necessary to solve any type of problem I could possibly ask you about this circuit. What is the current flowing through this resistor? What is the voltage across this resistor? What is the power dissipated by this resistor or this resistor? By following this strategy, you will see all of the possible answers to all the possible questions that I could ever ask you about this circuit. And the way we're going to analyze this circuit and keep track of all the different numbers that we're going to be interested in is with something called a VERP table. You heard that right. VERP tables. So here's what I want you to do on your paper. You're going to write VIRP across the top. That's going to be your first row. And then across the side here, we're going to put resistor 1, resistor 2, resistor 3, and then total. All right. Make your table look pretty. And we will okay. So how you're always going to set up these tables for any series circuit or really any circuit I could give you is down the rows you just list each one of the resistors. There's 3 resistors here, so we're going to have 3 rows to our table along with a total row on the bottom. If there was 4 resistors, you would do R1, R2, R3, R4, and total. If there was 2, you do R1, R2, and then total. Now, the beautiful thing about this table is it helps you keep track of the electrical properties across this single resistor. What's the voltage across it? What's the current through it? What's the resistance of it? And what's the power dissipated by it? Remember, that's what each one of these letters mean. V is voltage, I is current, R is resistance, P is power. Same thing for resistor 2, resistor 3. And then the total along the bottom is the total electrical specifications of this circuit. Here would be the equivalent resistance of the circuit. Here's the total current flowing through the circuit. Here's the total voltage across the circuit, and so on. Total power dissipated by the circuit. And as you can see here, all you have to do is identify the square that you want, and by filling in the table and filling in that square, you could answer that question. The current through resistor 2 goes right here. The power dissipated by resistor 1 goes here. Okay? So set up your table. Always draw the table. You won't always have to fully fill out the table. We're going to do that for this example. But as long as you can fill out the cell that you're interested in, you've answered the question that we ask you on the problem solving worksheets. Okay. All right. So here's what's given in this particular circuit. We have a 12 volt source and we have 3 2 kilo ohm resistors. Remember, kilo is the metric prefix for 1,000. So each one of these is equal to 2,000 ohms. Okay. So for this particular example, we're going to fill out the entire table. That way you can see kind of the logic behind filling out each cell or potentially each row by using our series circuit rules. And remember the rules we talked about last lesson. We know that the current everywhere in a series circuit is exactly the same. The voltage of the source is equal to the voltage drop across each resistor, and the equivalent resistance is simply the sum of all the resistors in the circuit. All right, so our goal is to fill out this table. If you'd like, take a second and try filling out this table yourself. Pause the video, but I'm going to go through and fill out each one of the cells in this table. So the first thing we do is take a look at the circuit that's given and use the information to first just fill in the cells that are already provided for us. We know the resistance of each one of the resistors, and each resistor is 2,000 ohms. That's resistor 1. You can call this one 1. That's resistor 2. That's resistor 3. Each one is 2,000 ohms. We also know that my computer just died. Is it back? It's back. We also know the total voltage across the entire circuit. That's the voltage of the source. That's going to be 12 volts. Here we go. And that's just our given information. What we do here is we use some logic and our knowledge of physics to fill out the rest of the rows on this table. So the first place I want to look is right here. Do we know the total resistance of the circuit? Another way to say that is the equivalent resistance of all 3 resistors in series. Well, if you look at this relationship here for series circuits, we know the equivalent resistance, Req, which is the total resistance, is equal to R1 plus R2 plus R3. Okay. Now, if this was like a part 2 Regents question, you have to always make sure you show all your work. You write your equation down, substitute in with units, 2,000 ohms, 2,000 ohms. There we go. And we can see that the equivalent resistance, what goes in this cell here, is 6,000 ohms. Boom. Okay. So now we have this cell here. Now, if a question simply asked you, what's the equivalent resistance of this circuit? You don't have to go through this whole table. But if it asks you, what is the voltage across this resistor here, I would recommend filling out the table so we don't get confused about all the different voltages, all different currents, and all different resistors. By using this table, you can see, here's all the information I want about resistor 2, and we can figure out that cell. So trust me here. Do the table, fill it out, and use it to find all the information that we're interested in. So that is the equivalent resistance. By the way, these 2 examples actually are in the typed Regents notes that I provided for you. Check in the circuit module. You should be able to see these examples there. Also with some of the other examples you did in the other videos. Okay, what else can we figure out about this circuit? Well, I can find the total current of this circuit. How? Well, we know the voltage, we know the resistance, and if you look at page 4 of your reference table, you know a relationship between the voltage, the resistance, and the current, and that is Ohm's law. If you look across any of the rows, if we know the voltage and the resistance, we can find the current. If we know the current and the resistance, we can find the voltage. If we know the voltage and the current, we can find the resistance, based on the Ohm's law relationship. So let's plug in what we know. If we're looking at the total section, we have to make sure we use the total resistance of the circuit. 6,000 ohms. It's a 12-volt source in total. What's the current? Okay. Flipping things around, doing some algebra, we get a current, make sure you can figure this out yourself, of 0.002 amps. Another way to say that is it's 2 milliamps of current going through this circuit. So now we have our next cell that we're interested in. Let's write it this way, so it's nice and tight. 2 times 10 to the minus 3 amps. Okay. But take a look at our rules for series circuits. If we know the total current, we know the current through resistor 1, we know the current through resistor 2, and the current through resistor 3. Because for a series circuit, no matter where I pick, the current is all the same. So by knowing the total current, I now know the current through each one of those resistors. Fill out each of those cells. 2 times 10 to the minus 3 amps. Nice. Okay. Now, again, using Ohm's law, we can find the voltage across each one of these resistors. Let's take a look at resistor 1. 2,000 ohms. We have 2 milliamps of current. What's the voltage across that resistor? I'm going to erase. R is equal to V over I. Let's look at resistor 1. That's the 2 kilo ohm resistor. We want the voltage, and we know the current. Again, doing some algebra, multiplying, we get V to be 4 volts. So we now know the voltage across resistor 1 is 4 volts. But in this particular circuit, this is 2 kilo ohms, this is 2 kilo ohms, and that is 2 kilo ohms. So it's the same problem solving here, same steps for each one of the resistors. Each resistor has a potential difference across it of 4 volts. Here I want to pause for a second and just make sure that we're all careful about the types of patterns we're seeing here. The only reason why the voltages are the same is because each one of the resistors are exactly the same. If the resistors had different values for their resistance, these voltages would not be the same. It's very important. But something that does hold for all series circuits is, if we add up each one of the voltages, if we add up each one of them, we should get our total voltage of 12 volts. 4, 8, 12, we got our total. All right, but what about that power, P? The power dissipated by each one of the resistors. Well, on our reference table, we have a bunch of different ways to calculate the power across any one of these resistors. We can do V times I to get power. We could do I squared times R to get the power. We could also do V squared over R to get the power. A lot of different ways to get there. But keep in mind that if I want the power for resistor 1, we have to use the specifications from resistor 1. If I want the total power dissipated by the circuit, we have to use the total, the numbers for our total values here. Okay, so let's start with the total power dissipated by the entire circuit. Okay, now for that, let's use P is equal to V times I. Okay. If you could simply use V times I would recommend using that. But the other equations still hold, and you can check them. You'll always get the same answers no matter which power equation you choose to use. So the power dissipated by the total power dissipated will be the voltage multiplied by the current. 2 milliamps. And the correct answer here is 0.024. And what's our unit for power? It is watts. Another way to say that is 24 milliwatts. That's the power dissipated, but that's the total power dissipated in the whole circuit. Okay. So for every second that goes by, this circuit burns 24 millijoules of energy. That's what that means. Awesome. And what about the power dissipated by each individual resistor? Well, we can look across and just make sure you use the correct equations that are on your reference table. The trickiest thing, erase. The trickiest thing about analyzing circuits is just keeping track of all the numbers. We've seen that for a few different units in physics. Just knowing which numbers we have to apply those equations to and keeping everything nice and organized, you'll always get to the right answer. All right, let's find the power dissipated by resistor 1. I'm feeling crazy, so I'm going to use this equation. P is equal to I squared times R. That's another valid power equation. So this is for resistor 1. We look over to resistor 1. We see 2 times 10 to the minus 3 amps multiplied by the resistance of resistor 1 is 2,000 ohms. Multiply it through, you will get a power dissipated by resistor 1 of 0.008 watts. That is 8 milliwatts. Here we go. Then you go to your table, fill it in. Nice. Okay. But then you look. Well, each resistor has the same resistance and the same electrical specifications. So these steps hold for each one of the cells for all the resistors. And again, the only reason why this is true here is because each resistor has the same resistance. If the resistances were different, the power dissipated by each one would not be the same. But here, because they're all 2 kilo ohms, we have the power dissipated by each one. And with that, we fully filled out our table. Now, no matter what they ask you about this circuit, you know the answer. What's the current through the circuit? Look at any of those cells. What's the voltage across this resistor? We know it. What's the power dissipated by this resistor? What's the total power dissipated by the circuit? We can answer all of those questions by simply using the verb table. Okay, you will not have to fully fill out the verb table for every single circuit. You only need to fill it out up to the point for the answer that you're interested in. Let's take a look at our next example, and we'll try filling out the table for that example. All right, take a second, write it down. I am going to erase this as smartly as I can. So we want to keep our verb table. you're going to make a new one for the next circuit. Here we go. And you know what? I think I actually need to. Hang tight, everybody. I'm coming back in a second. I hope everyone's doing well in their quarantine. I really hope I'll be able to see you guys soon, before the end of the year. Okay. Take a look at this circuit. This was actually a problem on a physics Regents. Here's the picture that was given. It was given that this is 50 ohms. It was also given, what does this A mean? This is an ammeter. It reads the current through our circuit. And the current was given to be 0.5 amp. This resistor was just simply labeled R. And there's 3 parts to this question. Part A, we want to find the equivalent resistance of the circuit. That's REQ. Part B, we want to find the value of resistor R. How much resistance is there in ohms? And finally, we want to find the power dissipated by the 50 ohm resistor. Those are the 3 parts of this question. Okay. So circuit is given, all these specifications. We want to find the equivalent resistance, this resistor, the total power. So you build your verb table. Here we have 2 resistors in series. So we don't need an R3 row. All we need is this total row. We have R1, we have R2, and we have the total. Now, we take a look and say, okay, well, part A, I want the equivalent resistance. That's here. For part B, I want the resistance of this resistor. That's here. For part C, I want the power dissipated by the 50 ohm resistor. That's here. So we don't necessarily have to fill out any of the other cells. As long as we get these 3 cells, we have our answers. I'm going to fill out the whole table just to show you how this all works. But as soon as we get to here, we're done with the problem. All right. So, first thing, let's look to see what's given. Well, this little box here says we have a 120 volt source. That's the total voltage. There we go. Across the entire circuit. There's a potential difference here. We also know the current. And we also know for a series circuit, if we know the current somewhere, we know the current everywhere. So if I know the total current, I know the current through resistor 2 and the current through resistor 1. Fill those in. We also know R1 is 50 ohms. You see anything else? I don't. All right. So I'm going to start by finding the equivalent resistance of the whole circuit, the total resistance of the circuit. That's part A. Now the first thing my brain does is, okay, let's add up all the resistors. Oh, I don't know this resistor. But if we look across this bottom row, I know the voltage, I know the current. I have enough information to find the resistance based on Ohm's law. R is equal to V over I. Page 4 of the reference table. R is equal to, looking across this row, 120 volts, the total voltage. Total current is ½ amp. Well, 120 divided by a half, quick sip of water. R is equal to 240 ohms. And that's the total resistance of the circuit using Ohm's law. This is all a puzzle. Here's to figure out how to use our pieces. Now, that helped us get part A. For part B, we can apply what we know about the equivalent resistance. The sum of this resistor and this resistor in a series circuit will get us to the equivalent, the total resistance. Okay. I'm gonna erase. Well, for a series circuit, Req is equal to R1 plus R2. There's only 2 resistors here, so we only have to add up those 2. We know the equivalent resistance now is 240 ohms. R1 is 50 ohms. And R2 is what we're interested in. 240 minus 50, that value is 190 ohms. That's here. We know part B. And for part C, we want the power dissipated by this resistor. Well, we know the current, we know the resistance, that's enough information to get the power. As long as I know any 2 of these in the row, I can get over to the power using one of the power equations. Come on back. There we go. I'm going to erase. Okay. The power dissipated by resistor 1. We know the current, we know the resistance. One of the power relationships is I squared times R. Okay? P is equal to ½ amp squared times the resistance, which is 50. Working this out, we get the power to be, do it yourself, watching you, 12.5 watts. Watts is our unit for power. And that goes here. And with that, we're all done with this problem. Notice how the verb table just kind of grounds us. Without that table, you're kind of looking and saying, I'm not really sure how to get the resistance of R. I'm not really sure how to get the power dissipated by this one. But by using the table, it kind of helps see what you have and how we can get to where we want. I hope I'm selling the table to you. All right, for the rest of this video, I'm gonna fully fill out this table. You're gonna see some relationships that I want you to see again, and it'll kind of show you how I think through these types of circuits. Okay, I'm gonna erase. All right. Now, let's go through. Can I find the voltage across resistor 1? I actually have a lot of ways we can do that, because we can use Ohm's law. R is equal to V over I. We can use the power relationship. Power is voltage times current. Once you really start filling out this table, you can use whichever way to get to the answer that you like. let's use power. Why not? Power is equal to V over I for resistor 1. The goal is to find the voltage. I know P, I know I, we can get to V. 12.5 watts is equal to V times the current, which is half an amp. Okay, dividing 12.5 divided by a half is the same thing as multiplying it by 2. The voltage is 25 volts across resistor 1. Let's put it on our table. Nice. Good race. Trying to give you enough time, not going too fast. Okay, another thing we know is that if I add these up, I get to 120 volts. That's a series circuit rule. The voltage of the source is equal to the potential difference across each one of the resistors. Let's use that relationship. Our goal is to find the voltage across resistor 2. That's here. Total voltage is 120. V1 is 25. Our goal is to find V2. 120 minus 25, we get, getting ahead of myself, 95 volts. There we go. And again, there's multiple ways to get there. I use these two, but you can just as easily use these two. R is equal to V over I. Plug it in, you'll still get 95 volts. All right, let's find the power dissipated here. Power. Let's do something a little different. We'll use V squared times R. I recommend using V times I, much less of a chance to make a mistake, but I just want to remind you of another one of the power equations here. For resistor 2, the voltage across resistor 2, notice I have 3 different values for voltage. The VERP table helps us keep track and say that, well, we know the voltage across R2, which we want to use to find the power dissipated by resistor 2. We've got to use 95 volts squared divided by 190 ohms. The power dissipated here by R2 ends up being 47.5 watts. Perfect. Okay, I'm just going to clean this up and erase that I don't need. Finally, we want the total power dissipated by the circuit, the power dissipated here and the power dissipated here. Let's use our nice easy relationship. Power is equal to voltage times current. Power, we're looking at the total row, 120 volts multiplied by half an amp. 120 multiplied by a half is simply 60. Total power dissipated by this circuit is 60 watts. All right, before I sign off, let's just take a look here for a second. Notice that we have 2 different values for the resistors for this example. And because we have 2 different values for the resistor, R2 being much higher than R1, the voltage across R2 is higher than the voltage across R1. But still, the sum of these two is equal to 120 volts. Notice the current still, even though there's 2 different resistors, the current is still the same through each one of those resistors. That's a rule for series circuits. Notice the power dissipated by each one of these resistors. The power dissipated by the 190 ohm resistor is 47.5 watts, where the power dissipated here by the 50 ohm is only 12.5 watts. By dissipating more power, that resistor will actually get hotter than the other resistor. Something I wish I could show you guys, if you set this up in your circuit, you could touch each one of these resistors and you will feel that this resistor, because it's dissipating more power, is warmer than the other resistor. Okay, and with that, you should have all the tools you need to solve some series circuit problems. Today I'm going to have you do some problem solving. I want you to fill out that worksheet that I posted. Use these tools. Tomorrow we're going to be discussing some rules for analyzing parallel circuits. You're going to find that we're still going to be using the verb table, but the rules that we use to analyze the parallel circuits will be a bit different. And we'll dive into that a bit tomorrow. Hope you're all doing well, and I'll see you in the next video.